Hi there, Mr. Chen here for Algebra 2. We're going to start a new section, 5-5, Function Operations. Grab your note taker and turn to page 131, and let's get started here. We have an opener here. Let's go ahead and read this together. In business, the term profit is used to describe the difference between the money the business earns, revenue, and the money business spends, cost. So profit is the difference, meaning you subtract what you make, the revenue, with how much it costs to produce that. A, Grooming USA charges $25 for every pet that is groomed. Let X represent the number of pets groomed in a month. Define a revenue function for the business. Now, I don't know about you, but this particular picture of this bulldog definitely reminds me of a dog that I grew up with named Buster. We're just going to call it Buster. That's a perfect name. So let's go and create a function. And we'll just use the letter R for revenue. How about that? And we're going to use function notation based off of the letter X. That represents the number of pets. So every pet we make is $25. So for every pet, we're going to use multiplication 25x. Not too bad. Next part. Materials and labor for each pet groomed cost $15. The business also has fixed costs of $1,000 each month. Define a cost function for this business. So let's do that. We'll use the letter C, which is the cost function. And it's based off of X again. And in this case, it costs us, the business, $15 per pet in material. So again, that's multiplication there. And there's a flat $1,000 cost to, maybe it's like cost to rent the place that you are borrowing the building or something like that. So that's going to be a simple constant of 1,000. Bam, there it is. So materials and labors is $15 per pet and $1,000 flat. Yay. Next question. Last month, Grooming USA groomed 95 pets. Did they earn a profit? What would the profit be if the business groomed 110 pets in a month? Let's look at the scenarios here, okay? I'm going to use some couple of scenarios for one of those situations here. So if scenario number one, we're going to look at our revenue with 95 pets. So that's what we're telling the audience. Hey, how much revenue are we making with 95 pets? Well, I'm using the function up here. Revenue up there is 25x, so it's 25 times 95. Punch that into your calculator, you'll get $2,375. And let's look at the cost involved with that. The cost for 95 pets is 15 times 95. I'm using the second equation, plus $1,000. Punch that into your calculator, you get 2,425. Oh no, the costs are more than the revenue, so this is a loss. We did not make a profit, did we? Dun, 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 dun. Side face. No profit. Let's take a look at our revenue with 110 pets with that scenario. Punch those numbers in. Using the first function, I'll get $2,750. And there's a cost involved, of course. We're going to punch that in as well. Using that formula, punch it into the calculator. Oh, yay. I actually make more money than the cost itself. So there's a profit of $100. Yay. For 110 pets serviced. Profit's good. Next question. Generalize or explain your procedure for calculating a profit for Grooming USA. Suppose you wanted to calculate profit for several different scenarios. How would you simplify the process? When we did that, we just compared, right? We subtracted, basically. So let's have a profit function, P of X, that equals to our two functions subtracted outright like that we did manually up there with our calculator. That's your function. It's very, very generic. Finally, at the bottom, a business breaks even when its revenue equals its costs. How many pets would Grooming USA have to groom in order to break even? And that's the question. So let's use our function up there. They say, hey, when do you break even? That's when you have zero profit. Right? Makes sense? That's when you break even. Using this function, I'm going to go ahead and put in 0 for P of X, our R of X, and our CX. Let's go ahead and move C of X to the other side by adding C of X. Hey, where does the C of X equal to the R of X? Put in those expressions that we got from above in part A and part B. C of X, of course, is 15X plus 1,000. And R of X is 25. Do a little math here. I'm going to move all the X's to one side. That gives me 1,000 equals to 10X. Aha! Divide through by 10. To break even, I need to service 100 animals or pets. That is the break-even point. All right. So that's kind of a good opener for playing around with functions. What can we do with functions, right? So the rest of this section involves basic operations involving the basic functions of adding, subtracting, multiplying, and dividing. That's all we're doing with functions. We're just getting used what's that word I'm thinking of? Repeating what we learned back in Algebra 1 when we introduced the idea of function notation and just basically using those polynomials and just applying basic properties to them, okay? Reintroducing the idea of function notation, that's what I meant to say. So, number one, we're going to add and subtract functions. The key when it comes to add and subtract functions is to combine like terms. Like terms are terms that have the same combination of variables. And if they do have the same combination of variables, you want to go ahead and change the coefficient, but you change the variable itself. 1a. We have a couple of defined functions. We have f equals to this function, 2x squared plus 7x minus 1. And we have another function called g of x, and it's defined as 3 minus 2x. 1a, all they want us to do is add those together. And we all know how to combine like terms. It's just a different way of asking the question. F, of course, is 2x squared plus 7x minus 1 plus 3 minus 2x. So it's basically looking at these 5 separate terms and you just try and combine them together. Are there any 2x squares anywhere? No, that's the only one. Fine, bring that down. No big deal. I like to go in different power orders. Hey, look, there's a bunch of x's here. Do we have any x's? Oh, yeah, we do. We have a 7x and a negative 2x. 7 minus 2, of course, is 5x. Well, this is all we're doing. You just have to get used to the idea of this function notation. And finally, negative 1 plus 3 is 2. And you're done. That was pretty easy. Yay. Okay. Next one. We're subtracting. Yay. Here, be careful that subtraction sign does affect the second function g. So the first function stays the same, 2x squared plus 7x minus 1. But the second function, you're affecting all of g. I would highly recommend you use parentheses here. If you're going to do it in your head, please be careful when you distribute that minus sign. And after you distribute the minus sign, make sure you double check your signs. So positive 3 becomes minus 3, and a negative 2x becomes a positive 2x. And just like 1a, you just combine like terms here. 2x squared stays 2x squares because we don't have any other any other x squares. 7x this time is added to 2x. So 7x plus 2x, of course, is 9x. And finally, negative 1 minus 3, we know as negative 4. So those can be combined together. Those are constants. Yay. And ladies and gentlemen, there's my answer for 1B. I think we're good with adding, subtracting, huh? You guys feel good? Let's go ahead and move on to the next operation, multiplication. Oh, it's a word problem. Great. Thanks a lot. Suppose demand D for a company's product at cost X is predicted by the function D of X equals to this ugly mess here, and the price P that the company can charge for the product is given by this function, P of X equals X plus 16. Find the company's revenue function. So some things to keep in mind here. We're trying to find the revenue. Let's do that. Revenue, in this case, is based off of the demand. Word problems are not easy. This time, times the price, right? When we have somebody or something ask for our product, you can give it to them by multiplying by the price associated with that demand. So this is different from the opener. This is where we have a different approach to just the revenue, okay? And the demand has built in the cost, X. So we don't have to worry about that directly. It's indirectly built into the demand. Y'all see that right there? It's built in. I can just see it right there. All right. So great. Let's plug in the functions because this is basically mimicking multiplication. The cost is built in. All right. Demand is that funny function. Let's go ahead and replace d of x with that funny function there. Let's put that in, negative 0.25x squared plus 1,000. The profit function is x plus 6. Let's put that in. Well, it looks like we have a product of two binomials. So first, here we go. First terms, whoa, just multiplying some funny numbers. So our revenue function is equal to negative 0.25 x squared times x. It gives me negative 0.25 x to the third. That's your first terms. Outer terms, whoa, 16 times that number is, and trust me on this one, 16 times that is negative 4x squared. Nice. Inner terms are next. 1,000 times x is 1,000x. This may seem very complicated, but the key here is that the cost is built into the demand. Therefore, you don't have to worry about the cost itself. Last term, 1,000 times 16 is 16,000. And when you get these four terms here, none of these combined together. This is the actual equation that a company might just use to predict what their revenue is based off of cost and profit. Not that exciting. I was hoping for something more exciting than that. Any questions about multiplication? All right. Next one's division. Identify the rule and domain for division for each pair of functions. They want us to divide f and g. So f in our first problem here is x squared minus 3x minus 18 divided by x plus 3. Now this is kind of interesting. Some of you might be tempted to reduce x's. Don't do that. These are polynomials. You're not allowed to do that. But before you just say you're done, you have to investigate to see whether or not this particular rational expression reduces or not. So yeah, you gotta factor. Ugh, gross, right? So the numerator, I can see that's factorable. What times what equals negative 18 when added together will give me negative 3? I mean, in my head, I'm thinking of all these possibilities, right, of negative 18. They include, of course, negative 1, 18, negative 2, 9, negative 3, 6. Almost there. How about negative 6, 3? Yes, there it is. So there's that combination. Oh, look at that. They purposely did that on so we can reduce it with the denominators x plus 3, right? So those reduce, that's allowed, and your function of f divided by g reduces to x minus 6. But we're not done. They're asking for the domain. The domain is what x values will make this rational expression true. Now remember what just happened. We reduced, we got rid of a denominator. And when it comes to fractions, the denominator cannot equal to 0. So we have to solve that. When we actually graph that back in another chapter, that actually became a vertical asymptote. This particular part is also not part of the domain. When you solve this, you get, after you subtract 3 to both sides, x cannot equal to negative 3. Ding, 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 ding. So this is your answer, x minus 6. And that thing right there, x cannot equal to negative 3, is your domain. Okay? That's something you have to keep in mind there. Next one, same process, different problems. Let's do f divided by g. Let's see what happens here. Ah, I see it. Parenthesize your polynomial so you don't feel tempted to cancel things. This is x minus 3 on top, and the denominator can be factored very easily as well. What times what equals negative 6 when added together will give me negative 1, the middle term? That's easy, 3 and 2. I like to do the numbers first and then worry about the negative sign last. There, oh, there it is, woohoo! Again, we've had things that cancel. And in this case, our final simplified division of functions is 1 over x plus 2 is your answer. But you do need to talk about the domain, don't you? The domain are where the factors in the denominator, because we can't divide by 0, you set them not equal to 0 and split them up and solve individually. X minus 3 cannot equal to 0. X plus 2 cannot equal to 0, and you solve them individually. Here we go. That's easy. That's easy as well. So our domain is x cannot equal, it equals everything else, but it cannot equal to positive 3 or negative 2. Okay? When you solve those individually. Bam. Easy peasy. Woo! How are we doing? All right. Oh, we might as well mention that. The 3 will cancel. That's a whole. Remember that from another chapter? That's definitely a whole. Now I'm going to call this one a whole as well because that kind of reminds me of all this stuff. And the negative 2 didn't cancel, but it's in the denominator. That's a vertical asymptote. Definitely. Most definitely. Something from back in another chapter. How are the domains of f plus g, f minus g, f times g, and f divided by g related to the domains of f and g? Well, here's the thing. The one part that we are worried about the domain is dividing by g. G, the function itself cannot equal to 0 in that division part. That's what affects it when it comes to division. Next page. Okay. So mentally, you're thinking, hey, are we done? Is this it? Are we done with this whole basic functions here? So this is a great time to take a little break mentally, and the answer is no. There's a new function, and it's called composition of functions. Write this down. Now, the word composition reminds me of something that you might do in your English class. Right? You know those composition books. That's where you put together a bunch of writings or some sample writings, right? And the symbol that we've done already is adding, subtracting, multiplication, division. This one has a different symbol. It's a open bubble. Okay, that is the symbol for composition of functions. Okay, it's a bubble or a circle that represents composition. The symbol for it looks like this: f of g of x. Ding, 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 ding. That's the symbol right there. And how do you say this? F of g of x is how you say that. The order of the two letters, F and G, are important. When you try to apply this rule, it looks like this: F parentheses G parentheses X close parentheses. Notice the G function is inside the F function. Think about the holidays, in particular Thanksgiving. Think of G of X as being inside the function of F as like the stuffing. Think of it as the stuffing. Think of F as like the turkey, right? During our holiday times, we put the stuffing inside the turkey, okay? So it's basically composition of functions. Think of it as a function within another function. Think of yourself as like a programmer. Programmers make things happen, and maybe you want to, if you're playing a video game, you want to make it, maybe the character comes across a particular area, they collect points. And that particular area might trigger another bonus, which create a bigger collection of points. So this is like a collecting points within another area where you collect more points. So it's like this, a function within another function. You're just making things a little more complicated, okay? Now, keep in mind the analogy of stuffing inside a turkey. Yep, sounds like one, doesn't it? Look at number 4. Number 4, I'm going to go ahead and do 4b first. Right now, they're asking me to find f of g of x, okay? G is the stuffing. It's inside f of x. Now think about this. X is a variable, is a placeholder. Think of that of what we're going to be doing next. X is the placeholder. Let's write that down. I know it's a variable, but you can put numbers in it for x. You can put other variables in for x, or you can actually put a whole combination of variables and numbers inside for x, right? So in this case, I'm going to do 4b first. Look at f. F is the turkey, okay? The function is 2x minus 1, okay? Let me write this down. 2x minus 1. Notice I left a big gap, blank area, parentheses, for the what used to be there, x. But x is no longer there. It's now g of x. That is the stuffing. Think of g as the stuffing, and that stuffing is 3x. That goes in right there where x used to be for f of x, okay? So you put it right there. And that's how you replace the letter x with an actual function, in this case, g of x. And now you just simplify and you're done. That's all you have to do. Now be careful, we're not multiplying with x, we're replacing x, okay? So here in this case, 2 times 3x is 6x minus 1, and you can't do anything else with that particular function, you're done. This is like adding, subtracting, multiplying, dividing, but with functions within another function. Not too bad, huh? Okay. Let's go back to 4a. Now this is interesting. 4a is like 4b, but instead of the letter x, they have the number 2. So in our answer for 4b, we got an expression. That answer is an expression. In 4a, our answer will be a number. There are two ways to do number 4a, okay? Sometimes you can use composition of multiple layers of things. I mentioned a stuffing inside a turkey. There's actually a delicacy that I've heard about for many years and I haven't had a chance to buy one. It's called a turducken. It's basically a chicken inside a duck, and that duck is inside a turkey, and it's like deboned and it's marinated, and they sell it, and you can just buy it and, you know, put it in the oven and roast it, and it's very delicious, I hear. So you have 3 animals in one without the bone, and you just treat it like a turkey with multiple things inside other things. In this case here, we have a 2 inside the G function. Then we have the G of 2 function inside the F. It's like triple layer here. So this is what you can do. You can just focus on the G of 2 part first and ignore the F. So we're going to do it 2 ways, okay? G of 2 literally equals to 3 times 2. You guys see that? Used to be X there. Now it's just 2. 3 times 2 is 6. Okay? 2 is the input. That's your X value. You put it into the equation, 3 times X. In this case, 3 times 2, you get 6. Guess what? 6 is G of 2. That goes into F. F of 6 is next. 6 is the answer we just got for G of 2. So you take F, which is 2x minus 1, and put 6 into there and clean that up. 2 times 6, of course, is 12. 12 minus 1 is 11. And there's your answer. That's one way of doing this problem. The other way of doing this problem is you can actually plug it into here if you want to. What, would you get the same answer if you put a 2 there? Oh, look. 6 times 2 is 12. 12 minus 1 is 11. That works too. Yay. So a couple of ways of doing that problem. Plugging the number into the individual functions first, or do the function composition and plug it into it last. It's up to you guys, okay? Same process. I want to throw in one more example to kind of get you guys used to this idea of using composition of functions here. All right, let's call this 4C off to the left here. We're going to go ahead and use the same functions, f of x and g of x. Oh, by the way, this is called fog. We call it fog. It's just something that we kid around about. So let's try FOF. Find FOF. This is kind of weird. FOF of x is f of x. You're putting a function inside itself. Kind of weird to think about, isn't it? You ever seen a dog chasing its tail? So here's what we're going to do. The outer function letter is f. In this case, it's 2x minus 1. And inside the cavity, I mean, where the stuffing goes, I'm going to put in 2x minus 1 in itself again. It's like looking inside a pair of mirrors, right? Inception kind of a thing. And here, you just have to clean it up and you're done. Again, we're not multiplying with x, we're replacing x, okay? X is a placeholder. When you clean that up, you'll get 4, my bad, x minus 2 minus 1, and then you get 4x minus 3, and that's your FOF, f of x function. It's kind of fun, actually. You get tired of adding, subtracting, multiplying, dividing. This is a very powerful function that you might see in programming and engineering, and it's done all the time. Okay. Number 5, write a rule for a composition function. Identify the rules for f of g and g of f. Now, I want to point this out. The first letter is always the turkey. Just want to let you know. The second letter will be the stuffing. So I want to point that out. Order matters here. So let's see what happens when we do fog and Goff. There's an old joke I used to say a long time ago with fog and Goff. You know, you should not Goff in fog. Hard to find the ball. I don't know if you got that horrible dad joke. Here we go. Let's do fog and Goff for number 5A and see what happens. All right, here we go. Here we go, here we go. F is x cubed. G, the stuffing, is x plus 1. Now, I'm not going to sit here, force you guys to do all that. X plus 1 to the third. You can actually simplify that by expanding and foiling. You'll get this. I'm going to save you some time here. This is x cubed plus 3x squared plus 3x and plus 1. Okay, that's what you get. Nothing too exciting. Goff is next. The turkey in this case is x plus 1, notice I said that, and the stuffing in this case is x cubed. Nothing too exciting. When you clean that up, you'll get, of course, x cubed plus 1. Oops. Highlight this and highlight this. Great. Yay. Nothing too special about those two, that particular pair. Let's do the second one, 5B. Let's do fog. This is the function f of x first, is the turkey. Notice the letter x is now parentheses. I'm going to put in the turkey, the stuffing, x minus 5. And this is a situation where, yeah, you could expand it for, you can take that answer. I don't really care, to be honest with you. Or if they actually simplified it, you'll get this as an answer. And trust me on this one. You know, expand and FOIL and add 1 at the end, x minus 5 times x minus 5, then you add 1, you'll get x squared minus 10x plus 26. Again, this is just more practice in this case. You can do Goff. And in this case, G is your turkey, x minus 5. Let's put in the stuffing, x squared plus 1. And when you clean that up, you'll get x squared minus 4. Oh, that's kind of cool. It's a difference of perfect squares, kind of interesting. But nothing too exciting here. Nothing too exciting. I'm going to skip number 6, if you guys don't mind. Any questions? Now, I'm going to do something very different. This is coming up in the next section after this section. When we do fog and Goff, we will learn, and I'm going to mention it now because I might as well get you used to it, why 5 even exists in the first place. It's kind of interesting. For the next section, 5-6, when you do fog and Goff, and if the result for both of them is the expression x, then they functions f and g are related. They're called inverses of one another. So let me put this down. If fog equals x and Goff equals x, then I'm just going to tell you now, f and g, you'll learn in the next section, are inverses. The idea of inverse is like functions, you know, like these operators. The inverse of add and subtract, the inverse of multiplication is division. But this is an interesting way of checking some of these particular polynomials. And the reason why I'm doing that now is because I'm now going to jump to the habits of mind at the bottom. It's kind of interesting that they are introducing something this early, but then they throw in an example that will give you x right here. And sometimes that's a dilemma some teachers have to worry about when it comes to teaching. Do I tell them ahead of time why they're doing this? Take a look at this habits of mind. Let f of x equals 1/3 times x minus 2 and g of x equals 3x plus 2. Find the rules for f of g and g of f. Are they equivalent? If so, does this prove that the composition of two functions is commutative? Okay. I'm not going to answer the actual question, but what happens when you do Fogg and Goff here? Let's see what happens. All right, first function is 1/3 times x minus 2. I'm going to put in the stuffing, 3x plus 2. That's the stuffing right there. And see what happens. Oh, okay. Not too bad. In this case, when I clean this up, I'll get inside the parentheses, 3x plus 2 minus 2 is just 3x. And then oh, this is interesting. When I take 1/3 of that result, I get x. Let's do Goff. And again, I'm kind of teaching what we're going to learn in 5-6. I don't know why they throw this in here now. It might be a little confusing, but it's just one of those things that is kind of interesting when it comes to this particular function composition. All right, 3x plus 2 is the turkey, and the stuffing is 1/3 times x minus 2. So here I need to multiply, and what I'll get when I multiply, distribute that, 3 and 1/3 is just 1. That's kind of interesting. 1 times x minus 2 is next plus, oh, look at that. X minus 2 plus 2 is also x. So it's kind of like a weird example, but they both equal to each other. Does this prove that composition of two functions is commutative? The answer is yes. Well, most of the time. I can't really say. I'll save that for the next section, okay? All right, let's get to the last page and just crank it out here. This is going to go a little faster, so thanks for hanging in there. Number 5. Ooh, we are given two functions, f of x and g of x. First function we want to do is add them together. Let's do it. 3x squared plus 5x plus 1 is f, and then add that to 2x minus 1. Combine like terms. I don't have any x squares. Fine, leave that alone. I do have some x's though. Let's combine those together. 5x plus 2x is 7x. And 1 minus 1 goes away. Yay, you don't even have to write that. My final answer is 3x squared plus 7x. Yay. Number 6, let's subtract. We have 3x squared plus 5x, same functions, plus 1. This time minus, and I'm going to use parentheses to show that we're affecting the whole thing, g of x, 2x minus 1. Distribute that minus sign, rewrite the problem to make your life easier. Let's do that. Here we go, minus 2x plus 1. And then, of course, combine like terms. Again, we don't have any other x squared, so 3x squared stays the same. But 5x minus 2x this time becomes 3x. And 1 plus 1 is 2 in this case. So there's that answer right there. Ooh, not too exciting. Number 7, we are subtracting, but this time is in reverse of number 6. Huh. Maybe this is a great time to think about subtracting two numbers in a different order. How is that going to change the final answer? Well, let's see what happens. This time, g of x is first, and we're subtracting f of x. In this case, 3x squared plus 5x plus 1. Let's see what happens when we apply the negative sign to that trinomial. 2x minus 1 minus 3x squared minus 5x minus 1. Negative 3x squared by itself. Great. The x's. 2x minus 5x is negative 3x. And finally, negative 1 minus 1 is negative 2. Interesting. Do a quick comparison to number 6's answer. Aren't they exactly opposites? You guys see that? So F minus G is the opposite of G minus F is the conclusion. That's it. Makes sense. Yay, multiplication is next. Let's do that. We are going to multiply F with G. F is a trinomial, G is a binomial. You know, why not bring back the box? Heck, that makes life easier for me. It's a 3 by 2 box. X squared, 2x plus 1 along one edge, and x minus 4 along the other. Sometimes it's kind of cool to just do it this way. It's kind of organizing. All right, x times that whole thing, x squared plus 2x plus 1 is x cubed plus 2x squared plus x. Great. Second row, I have negative 4x squared minus 8x minus 4. Take a look at your 6 answers here. I have 2 pairs that can be combined together as one pair, and here's another pair that are like terms. And my final answer is x cubed. Let's look at the first pair that can combine together. Negative 4 plus 2 is negative 2x squared. How about the second pair of numbers that are like terms? Negative 8 plus 1 is negative 7x. Great. And don't forget the minus 4. Woo! All right. Oh, division's next. Let's go ahead and do that one. We're taking f of x and dividing with g of x. Nice. Here's f of x divided by g of x. Now, you never know, can the functions be factored? And the answer is yes, but nothing cancels. So this is kind of an interesting twist. I do need to talk about the domain, though. The domain is the denominator. It cannot equal to 0. So in this case, when I add 4 to both sides, and by the way, that is the answer right there. There's nothing else you can do with that. When I move that to the other side, the domain is x cannot equal to 4. That is your domain. Okie dokie. Oh, number 10. We're flipping it upside down. Not that exciting, to be honest with you. Okay, fine. X minus 4 over x minus 1 squared. Again, nothing cancels here. So that is your answer. Simplified division there. And the domain in this case is look at the denominator. Here you cannot equal to 0. Add 1 to both sides. Kind of interesting. And in this case, the domain is everything you can plug in you want to, except x cannot equal to 1. A little boring. I was hoping that things would cancel. Maybe we'd get some asymptotes or some holes. Ooh, number 11, we're doing composition. F of g of x. The stuffing is g of x. We're stuffing it into f, okay? That's what we're doing. Composition of function. F is the turkey. Let's write down the turkey. 2x squared plus 5, okay? That big gap there is used to be x, and that's now the placeholder, and the placeholder is for the stuffing. Negative 3x goes right there. And you just simplify this thing. That's all we're doing. Negative 3x squared is negative 3 times negative 3 is positive 9. X squared. And clean that up, I get 18x squared plus 5. And that wasn't too bad. Yay. Well, 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 we are done. Thank you very much for joining me. See you next time. Bye-bye.